Hey folks, Dan here. Today on the MicroArch Club podcast, I am joined by Rick Altherr. Rick has worked at nearly every level of the computing stack, and we touch on many of them in this conversation. We start off at Rick's upbringing in the Midwest and how they learned about how machines work by tinkering on a theater organ. From there, we get into Rick's career, beginning with working on hardware performance analysis tools at Apple during the PowerPC to x86 transition, then moving to Google to work on everything from system software in the data center to flight control systems for internet satellites to open source FPGA toolchains. Rick's exposure to the hardware-software interface subsequently led them to security research, including their discovery of a widespread vulnerability in baseboard management controllers, and their collaboration with Laura Abbott to identify multiple vulnerabilities in an NXP hardware root of trust device while working at Oxide Computer. We round out our conversation with a deep dive into Rick's current work on quantum computers at IonQ. Rick does a great job of explaining quantum computing in relation to classical computing and outlines some of the current challenges of interfacing with these powerful machines. As evidenced by their willingness to talk with me for nearly 2.5 hours, Rick is passionate about opening doors for other folks in technology, and they regularly make time to do resume review, mock interviews, and mentorship sessions with anyone who is interested in talking with them. If you're interested, look for the link in the show notes. With that, let's get into the conversation. All right. Hey, Rick. Thanks for joining the show today.
Yeah, glad to be here.
Absolutely. Well, we've obviously chatted a little bit before the show, and I've also followed some of your work for some time, including some of your talks and appearances on other podcasts. Actually, earlier today, and I think I mentioned this before, I was listening to your On the Metal episode, which definitely had a lot of good tidbits in it, but also one of my coworkers in my day job, Chris Gamble, has a podcast, The Amp Hour. And you were on that, I think, a few years ago now. So I've definitely, so I've definitely run into you in a few places. But super glad to have you on the MicroArch Club, and I think we'll have a lot of fun stuff to get into today.
Yeah, sounds great.
Awesome. Well, I know you've listened to a couple of the episodes, so you know a little bit of my preference for kind of starting off in the beginning with folks. I'd love to learn what your introduction to computing was and maybe what some of the first machines that you interacted with are.
Yeah, I mean, that is a little tricky in that it kind of depends on how you define computing. So, like, my family has a history of auto mechanics, and so you get into things that are like not quite computers, but kind of are computers. You know, like how a transmission, like an automatic transmission, works is a hydraulic computer, effectively. And so I had some exposure to those kinds of things, but probably I spent most of my time actually with learning about electronics and mechanical systems through my grandfather. Before I was ever born, like when my mom was a teenager, he ended up buying a Wurlitzer Hope Jones unit orchestra, which is a theater organ, and installing it in their house.
Oh, wow.
And so I learned growing up, like, this was just the thing we had. It was there we had for demonstrations to, local school groups and things. And I was small enough that I could climb through to go in and fix all of the stuck electromagnets and, like, do all sorts of adjustments and things, and learned about it a lot about how to build, relay logic type things, and that stuff. So learned a lot from my grandfather, who was very much a perpetual tinkerer in electronics, mechanical things, all sorts of stuff. And then really get on into computing. I was probably like 6 or 7. My dad ended up getting a job as a computer salesman because that was an actual job at one point.
Right.
And so I got to periodically go into the computer store after school and just kind of hang out and learn a lot. We had a 286 at home, got to play, the video games and things like that, and really just kind of took to it. And so I spent a lot of time, learning about programming languages and how the system worked, and as much as I could. And that really progressed up through high school and everything else. eventually got my own computer so that I would stop breaking the family computer. And my first job actually ended up being working at a ISP locally. So
Oh, cool.
they were like in the late 90s in the rural areas, you'd have these combination like computer stores slash web development firms slash ISP. And so I was more on the computer repair side of things, but I was also doing the ISP side and got a lot of exposure to just how the internet works and that kind of stuff. And yeah, so that's a lot of where I started. And then, ended up going to college for originally for a computer engineering degree, but then decided pretty quickly that I didn't like doing all the math for the electrical work, so switched over to computer science, and yeah, a lot of it just kind of kept going from there career wise.
Gotcha. With the earliest machine that you had for yourself, what model was that?
I believe it was a 8086 clone. I don't
Okay.
remember exactly what it was. It was not new, right? It was
Right.
definitely like a hand-me-down that nobody wanted because everybody had 386s kind of thing.
Absolutely. Is the so you kind of got started in maybe programming your family's computer and then eventually your own computer. Was that mostly in a higher level language like BASIC or something like that, which it may be comical to call BASIC a high level language now, but as opposed to getting down into assembly and in the lower level parts of the hardware?
Yeah, I mean, growing up, like I grew up in rural Ohio,
Okay.
in Northwest Ohio. I didn't have a lot of people around that knew anything about computing, right? So like my dad working at a computer store was much more focused on how you use computers, not how you do programming or anything else. So mostly I had copies of QBasic and what was available in terms of documentation that came with DOS, and that was it. I didn't really have access to a C compiler or any of those things. That really didn't come around until I was a teenager when finally that kind of thing was available. And by that point, I already had my own computer and was working at an ISP, so I had internet access. That was a very big change. But before that, yeah, I was writing complicated basic programs, trying to understand more of how the hardware actually worked, but was very limited just by what was available. I mean, even going to the local library, there wasn't any information. Like programming books were not a thing that the local library was going to carry.
Right. And at your high school, was there any sort of computer science education, or was this strictly kind of like outside of school?
There wasn't until like my junior year, at which point, um, like they had a computer lab, but it was very focused on like learning to type, using Word and Excel, kind of, more basic computer user skills than development stuff. So there were no computer science classes. There was, but as we got into my junior year, the person who ran the IT staff knew that there were a couple of us who actually had a lot of interest in computers and things. And so he worked with the local community college to have us do the Cisco CCNA courses.
Oh, cool.
But we had to show up at 7 a.m. before school, and like we did CCNA before we actually started our regular school day. And so we did all that. Neither one of us actually ended up taking any of the exams for it, but we definitely got all of the exposure to like, here's how you set up routers, here, all that kind of stuff. But that was the extent of it. That we didn't do any AP courses or anything else. Mostly it was just a small set of people that happened to have computers and that kind of interest, sharing skills and things behind the scenes. At that stage, like in high school, I probably was more known for running the server that hosted like TI Net and TI News for the calculator programming stuff than anything
Right.
else. Yeah.
That's really interesting. I feel like one of the things that maybe gets discounted by folks who don't have that experience. So I grew up in the Southeast United States, and there is just a really big geographic difference in terms of computer science education. I graduated from high school in 2015, and there was no computer science at the school that I went to, and it was a fairly good academic high school, but it wasn't really top of focus. And I do think in the past 5 years or so, there's been even more of a shift. But I think there is a pretty big geographic difference potentially between the coasts and somewhere like the Southeast or the Midwest.
Oh, absolutely. I haven't looked at what they're doing at my high school recently, but certainly I wouldn't expect them to have much of a formal computer science curriculum. It's not top of mind. They graduate maybe 100 students a year, and that's not like a private school or anything. That's just the county school system. Like that's
Right. Right. Well, so then you go to college and you decide to study computer science. What was that decision like, especially coming from, a background where there wasn't a lot of folks that were into that, or it wasn't necessarily, I don't know if it was seen as a kind of like viable career path?
Well, my parents saw that from, my dad's job working in computer sales. Like it was obvious that computers were an up and coming thing. And my dad actually had interest in computers going back to when he was graduating from high school and going into college. He just couldn't afford college at the time. And so he never actually got a college degree, but he got a little bit of exposure to it through kind of the math to computer science path that was more common back then. And so they understood that there was utility there. And that it was an up and coming area, that it was probably a good place, as far as career wise. And then I had a lot of interest in it. It also helped that my brother had decided when he was going to go to university that he also decided to go to computer science. And later my sister also went for computer science. So all three of us went for computer science. But it was really just I like doing this and I don't know what else I would do. And my parents were fairly supportive of that. I was going to a state school, so tuition and everything was pretty affordable. And it was just like, sure, why not? We'll see how it goes and see what happens. And turned out it worked really well for me. I really do. I knew I already enjoyed computers. I didn't actually know what working in computers would look like. But it seemed like I was asking a lot of the right questions to go ask more and figure out where I wanted to work in that space.
And did you find that the computer science curriculum was fairly strong, and was that kind of a foundational part of how you went on in your career, or did you feel like that a lot of the kind of skills and things like that you gained were mostly outside of the classroom, and those were the biggest contributing factors to what you ultimately went ahead and did?
It's a mix. So I went to University of Cincinnati, which is a pretty well-regarded engineering school. Certainly not Ivy League or anything, but reasonably well-regarded. And their computer science program is decent. I felt the curriculum was... When I started, I was ahead of the curriculum. There was definitely a lot of areas where I learned more through the curriculum. But just like Nathan, past guests, talked about, his school did co-ops. Actually, University of Cincinnati is where co-ops was created. So
cool.
The entire, all of the engineering schools do usually it's a 1 quarter on, 1 quarter off. Computer science tended to do more of a 6 month on, 6 month off. And so I ended up through that getting an internship at Apple. And so I went from I really like computers and I'm learning about programming and some of the, details of how the computer works, to I'm working in a group that actually does performance analysis of up and coming processors for Apple computers. And so I ended up just kind of leapfrogging everybody else at the school in terms of what I understood and everything. So it was this mix of would I have done well just being in the curriculum there? Yes. But honestly, the co-op really brought a lot more to the table in that regard.
That makes a lot of sense. How did you end up getting into the performance analysis kind of aspect of Apple?
So my friends and I dispute exactly this exact sequence of events here, but essentially what happened is there was a centralized office that helped you with co-op placements, and they were generally well known as being absolutely terrible at their job. So often it was you had to negotiate your own internships or co-ops with a lot of companies. And so they often were in the area, in the Cincinnati area, it'd be like going to GE or Procter & Gamble or whomever. And occasionally someone would end up with these ones far, somewhere else. And it just happened that one of the other students that I knew got an internship by somehow his resume ended up at Apple. And as far as we understand, it wasn't supposed to have happened, but it did. Um, and he ended up getting an internship on that from that working with their compiler team.
Mm.
And from that, it was, hey, there is he's coming out and it's a 6-month internship, not 3 months during the summer, right? Like they could have interns throughout the year effectively. So that team started to spread the word internally that they could pull more people in from the school, which then turned into, well, hey, who would you refer as someone to come in? So that person referred a friend of mine who ended up being he was an electrical engineer student. And so he ended up coming in on the hardware development side and working with the architecture performance group team, which is, and he ultimately referred me as someone else who could come in more on the programming side and the system analysis side. So that's how I ended up there. But it sort of built around, there was just a manager that really understood how to get internships moving through the system and get them brought into this organization and kind of fan them out through that. And we actually ended up with a lot of people there. There's probably a good 7 or 8 year timeline where people from University of Cincinnati were coming into the Mac hardware group via that.
Oh, wow. That's awesome. What did you work on during the co-op, and then ultimately did that end up being what you worked on when you joined Apple after university as well?
So the very first thing that I got as an internship project was validating that the performance counters on the PowerPC 970 actually counted the microarchitectural events that they claimed to count. Which turns out I had no idea what a performance counter was. I had no idea what most of these events were, and I had no idea how I was going to write code to trigger these particular events to even do validation. So that was a very challenging project. I did actually ultimately figure it out, and through that, I actually ended up writing the documentation for IBM on how their performance counters worked, because all of their documentation was wrong. And they just eventually were like, here is the FrameMaker source code, please update it and we will ship whatever you write. And so that taught me a lot about how the processor worked, very, very detailed inside. And that was on, PowerPC 970, which is the G5, which is a very complex out of order processor. There was just a lot going on. And so I kind of, that was how my internship kind of leapfrogged me ahead of my classmates, was just like, I had industry experience with bleeding edge processor microarchitectural design right up front. And so I ended up staying with that team for a long time. Actually, they hired me on and I worked there for 4 years. I started in that area, I moved a little bit more over to developing the tools. So that team was kind of this cross-functional thing where it was part of the Mac hardware group, and it was definitely focused on understanding the performance of Mac hardware systems. Mm-hmm. They were looking at the new systems that were being developed to kind of inform and work with the vendors on how we might modify things to improve performance. But they were also working with third parties on how to tune software for those new platforms. And so the third part of it was the developing all the tools for all Apple developers to be able to do performance analysis work and come back with it. So I ended up moving more into the tool development side. That team notably released was the CHUD tools, the Computer Hardware Understanding Development Tools, but it was actually a reference to the terrible 80s movie. But the whole idea there was, these are the tools that you can use to figure out how your application actually is running on the hardware, beyond sort of like your basic statistical sampler of CPU time. This was, how do I actually dig in and find out what's happening at microarchitectural level, what's happening, throughout the system, and raising that information in the way that you kind of expect from Apple. It's like, here's your code, and here's the tooltip that tells you exactly what's happening on this line, right? That was kind of the thing, and so I ended up being tech lead of that team for a couple years through kind of the later versions of that software, and worked on almost every product that Apple shipped from 2004-ish to 2009.
So you were right right in the middle of your time there was the PowerPC to x86 switchover. Is that right?
That is correct.
Okay.
Yeah, that happened like right as I was joining full time, like my
Mm.
last internship to full time. I joined full time in 2005, and yeah, we had development units that were hidden inside G5 cases and all sorts of things. It was kind of a big deal. Very big change for our team, certainly. Like, you can imagine that when you're doing the performance work at that level,
Right.
digging into the chip details, going from PowerPC to any other architecture is a massive change in the tooling to understand. The conceptual model of how the processor works probably isn't that huge of a change, but the exact details of how you control performance counters, how you actually know the subtle details of what's happening through execution units, etc. And took a lot of time to build up that knowledge again for the new platform.
Absolutely. Did y'all have kind of an abstraction layer over the PowerPC that allowed you to kind of like write a new backend, if you will, for it, or was it mostly?
Oh no, not
No.
at all. It was entirely written to support PowerPC and nothing else. So I mean, and keep in mind that with Motorola slash Freescale and IBM, we had a very close relationship to the extent that if you install the CHUD tools, it actually ships full cycle accurate simulators for G4 and G5.
Oh wow.
It's for running execution trace or like instruction traces of small snippets, not like booting a whole system. But we
Right.
had that level of relationship with them where that was just there. We shipped the entire assembler reference. So when you were looking at an instruction, you could just click show me the instruction and it would pull up the PDF to that exact page, kind of thing. And working with Intel, it took a while to build up all of that because we had just never assumed that we would change to a different architecture. That's kind of the classical problem with changing architectures is like you just build up all these subtle assumptions about how the system would work. And a lot of folks are more familiar with the like, oh, you're running on big endian and you're switching to little endian, you're going to have a lot of pain.
Right.
There's also just a lot of pain for. I wrote my entire stack assuming that all my instructions were 32 bits.
Mm-hmm.
Oops. And then we turned around and did it again as the iPhone started development, where now I had to do ARM. I ended up writing an ARM disassembler over a weekend to support the iPhone program, right? Like, we were trying to make that happen as fast as possible and shoehorned it in. And at least we had done it once with x86 at that point. But yeah, going to 3 different architectures that we supported was the code base started to get quite ugly at that point.
Right. Right. Did y'all have more or less heads up with the iPhone in terms of the transition coming? Because it sounds like y'all might have not had a ton of heads up on the PowerPC to x86 transition.
Apple is well known, very tight-lipped,
Right.
both externally and internally, and very siloed. And so the x86 development started as a small team somewhere else, not in the hardware group, kind of doing their exploratory work. And then eventually the hardware project started, and then eventually the performance team came in. And the iPhone kind of happened the same way. It started with some folks from iPod kind of specking out what the system would look like, etc. And by the time we got pulled in, they already had engineering units, not form factor, but like prototype board units. They had a software stack that was booting. They had been doing a huge amount of work without us. And so we got brought in late where it was actually, we're seeing problems that we need your tools to understand what's going wrong. And we said, well, now we have to go actually figure out how to pull out performance information out of the system that you're running on.
Right.
So give us a couple months. You don't have a
Right.
couple months, iPhone was specifically like to the extent where I had to sign a separate NDA just for iPhone. And I actually had 2 office locations because I had one in Building 5, which is where the Mac hardware group was, which is my normal office. But then Building 2 was where they were actually doing all of the iPhone development. And so I had to go up there to a different desk for any time I was working on iPhone related stuff.
Interesting. Were there any, performance bottlenecks or anything like that, or any bugs that y'all encountered? I guess, not just in the transitions, but just in general in being the authors of this tooling, where y'all had, a vendor or a third party or someone like that come in and say, hey, like, what's happening here? Your tool is telling me that, there's a performance bottleneck, but I don't understand. Any particularly interesting ones?
I mean, we worked with the Adobe folks on Photoshop a lot, and so there were always, subtle things that came up there, but they also were quite well versed in the what could happen, right? Like how their software worked, and we're working on very core loops. I do remember a lot of game developers coming in. The Mac is not particularly viewed as a game platform, at least it wasn't, especially back in the PowerPC days, but I remember sitting down with the developer who was porting one of the Rock Band games. And we were just like, why is this burning 3 cores 100% and still struggling? And we looked, and the game was written assuming the Xbox platform, and that it was just going to have 3 cores. And so they had just written 3 busy loops, that one on each core, that ran, it was like one was disk I/O and one was network I/O and one was everything else. And this does not map well, right? Like, it was entirely assuming it was going to run on a Windows NT based system, and how critical sections worked and all that, and it was very terrible. But I also worked with, like, on G5 was used to build a supercomputing cluster. So I ended up getting a lot of, here's a application that they're running. You don't get the whole application, but you get this tiny piece of it. Like, iterate on that. We used to do a lot of demos for, we would work a open source program to show how you would go through the process for talks at different conferences and things. And I remember one time we looked at an open source program called Celestica. It's a star system simulation where you can travel to different planets and see the simulation of the orbital motions and things. And we had all these different options. We'd show how you could do, replace calls to sign with table estimations and, basic stuff. And at the end, as we're getting down further and further into here's how you can reorder your instruction scheduling to be able to be tuned for G5 behavior. We're like, and now you're at 16,000x performance.
Did y'all end up making any upstream contributions?
Oh yeah,
to that
yeah,
project?
we always did. That was the thing, is we would do the work with the
Cool.
to do this, and we would send it all upstream, and often they accepted it. They were just they were very, very gracious on it. We did that with a lot of projects, actually.
Awesome. So 2 questions, kind of wrapping up your time at Apple. One, are the from my research, it looks like the CHUD tools are still used today by Apple developers?
I'm not entirely sure. I
Okay.
honestly haven't paid attention to the Apple platform for a long time. When I left in 2009, there was a big push to fold the CHUD tools into instruments. And so in some ways, when you're using instruments and you're using time profile in there, it's actually using all the same infrastructure. It's just kind of through a different UI.
I see.
So, people are using a lot of the pieces, but not necessarily through the front end.
Mm-hmm. Absolutely. And so when you did decide to leave, I think you said 2009, was it mostly you wanted to go work on something else? Or was there, I know you ended up going to Google. Was there something particular about Google that was alluring at that time?
No, actually, I followed a friend who left from Apple and went over to Google. And so I just had a good path there and kind of knew there were interesting things happening there. But I was looking for something different to go do. The CHUD, or the architecture performance group, had been located in the Mac hardware division and got moved, split up and moved in. The CHUD tools ended up reporting to developer tools, and we just had a lot of culture clash. Developer tools from the Core OS group was very much of the opinion that you were there to work on software, and it was there to work with the operating system, and you didn't actually care what the hardware was too much.
I see.
And of course, the entire thesis of CHUD was, if you know what the hardware is, you can do a lot more. So we just kept running into issues of I need a kernel extension to do these things. And they're like, you can't install a kernel extension. Sorry.
Right. Gotcha. So you follow your friend to Google, naively in my mind, I think you also did some performance work at Google, but, you're kind of going from this focus on, Apple, especially at that time, I imagine was mostly, a single machine that you're kind of analyzing and seeing how the CPU or other components in that system are working. And then Google is, both large scale companies, but Google is very different in that you're working with large network systems where you're kind of, analyzing perhaps at a data center layer. Was that kind of like did you find that the skills translated quite a bit? Or was Google kind of like walking into a new environment for you?
Some skills translated,
Okay.
but certainly, I mean, it's hard to answer that question really. And anybody who's had the privilege of working at Google will relate, and everybody who hasn't, it's just hard to explain. Not only is the scale of the systems that you're working on so vastly different, right? Like you said, it's not looking at 1 or 10 or 1,000 machines anymore. It's looking at tens of thousands of machines, hundreds of thousands of machines. And so there's that angle, but also everything is managed in-house through bespoke systems, and they're not intended to be shipped to customers. Whereas like with Apple, yeah, it was all a big proprietary stack, but there was definitely a focus on you have to ship things to customers. And so you can do some hacks, but you have to make it a little pretty to make it, acceptable to the customer. With Google, you could just, as long as it worked, it didn't matter too much. Like you needed it to be reliable, but it didn't have to be pretty
Right.
necessarily. But it also meant that you didn't have to abide by any industry standards. You didn't have to the design space was wide open as long as you could justify why to do it that way. And so, you put those two together and you get into odd decision matrices where you're like, we're doing it completely different than everybody else does, but that's because it saves us this amount per machine, which times the number of machines makes a huge difference. We used to talk about like the team I was in wrote a lot of the software that runs on every single server in Google's data centers. So there's system daemons that manage the hardware and do telemetry and health monitoring and a variety of other things. But we at one point did a calculation where we figured out if anyone on our team saved 1 megabyte of RAM, we paid for the entire team's salary for the entire year.
Oh my gosh.
Now, I mean, it became difficult to actually save 1 megabyte of RAM because we had already done a lot of that optimization to fit in there. But that was like the stakes, right? The scale of things changes how you think about the problem a lot.
Right. That's actually interesting. The episode that comes out tomorrow is with Matt Godbolt, and he spent some time working at Google as well. And one of the things that we talk about on that episode is kind of like having that scale where like saving a meg of RAM is having that large of a cost implication. Provides a lot of justification for working on some interesting things that just wouldn't make sense economically at other companies. Did you have any examples? I mean, maybe that is one right there, right? Of like saving a bit of RAM. But did you have any examples of things that you worked on or you saw folks working on where they got to kind of like go down that optimization rabbit hole because of the sheer scale of the systems y'all were working on?
Oh, absolutely. It happened all the time. Things that come to mind. So, you know how when you type in on Google search, it autocompletes for you?
Right.
I had nothing to do with that feature. However, that feature was burning so much CPU time in one cluster that was depending upon a search indexing that was running in another cluster that they kept coming to me and saying, your software is saying that there are problems on the system and taking machines out, which is causing our service to be unreliable. We can't actually launch our service publicly.
Hmm.
And that led down a digging through so many layers of the system and ultimately figuring out that there was a bug in the CPU scheduler in the kernel where I was not being given enough CPU time to actually do the work because the system was so heavily overloaded. Like, I've never seen load averages in the 500s ever again.
Right. Right.
So there were things like that, but also things like, you know how PCI Express has a lot of pins on it, and some of those pins are not commonly used, right? There's like JTAG and there's other things, and there's
Right.
actually ones that are reserved for future use. Well, we justified why we should dedicate a pair of those to be a USB pair so that we could have USB out to our expansion cards to talk to different things. I worked on a system where we used SRIOV. I don't know how familiar folks are, but like with PCI Express, you can do I/O virtualization where you make a single PCI device look like multiple devices. So you can share them with like virtual machine or like guest virtual machines or things. And we use that feature to emulate a MRIOV, which is where you have multiple computers attached to a common PCI Express fabric, and then we use PCI Express switches. So I like figured out and worked with a team where we ended up booting 8 machines off of a single network card that they all shared. It's just like
Right.
not a problem that anybody else is ever going to look at, but it was a way of looking at how would you deal with bandwidth problems and the scale of how much cabling and deployment of the system, etc. So yeah, lots of edge cases. I mean, it just probably goes on and on and on. And some of that work ended up coming out through Open Compute project. Eventually Google joined, and some of the design work that came out. Even OpenBMC is a case where, funny story on that one, we were working with Rackspace on Barrel-i G2 is what they called it, and Google called it Zeus. But it was a Power 8 system, IBM Power 8. And because it was going to be public through Open Compute project, and because Rackspace was going to use it, they wanted to have a common BMC or baseband management controller that that you would normally find on a server, because that's how Rackspace's infrastructure is designed, but Google's is not. And we were trying to figure out how we were going to support it internally, and my boss was in charge of talking with AMI about their software stack, getting a license for Mega Rack to run on this. And I made a friendly wager with him one day that after he had been trying to work with them on getting just a price quote, I said, I bet I can actually get Linux to boot on the BMC faster than you can get a quote from them. And I did it in 2 days, and it took like 2.5 weeks for him to get a sales quote. So by the time he got a quote, we actually had a fully booting Linux stack, and that's kind of how we ended up working with the OpenBMC folks. And I ended up working in that space of getting a bunch of the big industry players at the time, Facebook, Google, Microsoft, IBM, all to come together and actually form that as a proper project under Linux Foundation to, here's how you actually build an open source management stack for these systems. But that was also driven from a need for, solving some of these problems at scale and starting to work with other players. But you see a lot of these things. We built 48 volt to point of load voltage regulation. I think no one else does this. But that's going from like 48 volts to directly to your CPU core in one stage of conversion. But the efficiency makes a lot of sense when you're at the scale of Google.
Right. So you talked about BMCs, and we're definitely going to get back to that in the future. But can you talk a little bit about just like the general architecture of Google servers and what role a BMC is playing? I guess in Google servers, but also more generally.
Yeah, the concept in like a server is that the main CPU is usually doing some work that's owned by some team. And they have applications that they're dealing with and whatever. But often it's a separate team or organization that's responsible for the hardware management. So it's like keeping the machine physically turned on and running and reporting the health information about hard drives and fan failures and that kind of stuff goes to your IT or data center operations folks, whereas application type failures go to the team who actually is using the machine. And so a long time ago in a faraway planned Intel worked with a couple of other companies to create IPMI, which specifies how a BMC exists on a system. And it really starts as like doing environmental control and power monitoring and having a way of querying that type of information from the host processor. So it's about offloading all of that. And one of the key aspects is that you can access that information even if the host machine is completely locked up or turned off. So you can also do things like reset the system. You can power it off. You can power it back on. And over time, that feature set has grown more and more and more to the point where you have an integrated KVM support. So you can actually just go to a website that's run by the BMC on that on that server board. It's actually an entirely separate computer on the same motherboard as the main system. But you can go to a website that's hosted by that, get a UI that loads and gives you a display of what the actual console output looks like from the, if you hooked up a monitor on the VGA port, you see the exact same thing, and you have
Right.
keyboard and mouse control, and you can select like an ISO image, like a CD image, and have it be mounted as a virtual CD-ROM drive on the remote system. So you can do like complete from scratch OS installs
Right.
remotely. And so there's a lot of useful features for that. I mean, it falls under a lot of larger category folks talk about as lights out management. The idea that the lights are turned off in the data center. Nobody has to be there. This is how you know how you manage and interact with the systems without having to physically be there. And also knowing when you actually do have to go physically touch them. Oh, a fan failed. I got to go replace that.
So is the whole interface like the HTTP API that it sounds like you're explaining there? Is that part of IPMI, or is that just kind of like vendor specific implementation?
So IPMI is old. IPMI came out of the late 90s, and there was a couple revisions of it. And it is its own bespoke protocol, right?
Okay.
It's something that you talk over TCP and have very specific data frames and stuff. And so that's when you run like IPMI tool on a Linux machine or something like that. You're speaking this custom protocol to that device. So the web UIs came as a way to like introduce a more friendly way of doing it through the web browser once the web had really become a big thing and people realized that you could run a web server on one of these as a friendly thing. But yeah, it's more bespoke. There's been a change in the past 10 years there is a later standard called Redfish, which is kind of reimagining IPMI as a REST API. So it looks more like you'd expect for a web interface as an API, but it kind of has the same data model as IPMI. It's like you ask the system, how many sensors do I have? And then it comes back and it's like, oh, well, which ones of those are temperature sensors? Like here you...
Right. Is the are IPMI or Redfish or any alternatives, if there are any, are they ever used outside the context of data centers, or is this mostly a pretty focused protocol?
I mean, it's mostly used for dedicated server hardware. Whether that's used in a data center or not kind of depends. I mean, I have the machine I'm on right now happens to have a BMC and can actually do all this stuff. Do I use it in my house on a regular basis? No, not really.
Right.
But yeah, it tends to be focused on that out of band management, lights out management type situation. And so that mostly finds its way in server gear. Sometimes you find it in like industrial control equipment that's based on PC stuff. Like there's various applications for it, but it doesn't show up in usually doesn't show up in your average PC. Although there was there is a parallel in laptops. Intel has what they call AMT, which is not a BMC, and it doesn't really speak IPMI, but it offers most of the same functionality. So you can do remote management of laptops. And again, it's intended for an IT department to be able to fix your laptop for you from wherever you happen to be.
Gotcha. One of the things that kind of stuck out to me in your description of BMCs was you led with the like organizational component of it. And obviously there are some technical benefits to the isolation and, like you said, the lights off management and that sort of thing. But I think that is always an interesting way to approach any system design as, oh yeah, there's a different team that does that and is responsible for that. So we literally have, a different computer for them. I haven't heard it explained that way. So, but it makes a lot of sense.
I mean, it's a long-term thing where I don't know that was the original intent.
Right.
However, a lot of solutions end up growing according to how organizational lines fall. And so that's how a lot of the feature set has developed for BMCs over time, which has interesting implications because the security model did not evolve the same way.
Right. That was a little bit of foreshadowing, perhaps. But while we're still at Google, you spent time working on these servers and the data centers and that sort of thing. I think I also read that you spent some time working on flight control software. Is that right?
Yeah, I got after spending all the like 5 or 6 years working on servers and hard drives. I was the manager for the hard drive team, and had done a lot in that space. I wanted to try something different, and Google being Google, it has a lot of different areas that are going on, and it just happened that around that time was just before the whole shift to being Alphabet and having the other bets, but X had existed for a while, and there were some of these more grandiose, like very different ideas, not the typical Google development things. And one of those was building a satellite internet project. So a LEO constellation of satellites that provided internet access. And if this sounds a lot like Starlink, that's because it is. This is actually a predecessor project, and through a series of unfortunate events, the team forked, and part of them went to create Starlink. So common lineage there. But yeah, I was working on flight control systems and a lot of the high-level architecture for how the system would work. When you're designing a satellite, you kind of have the part of the bus. They call the satellite the bus. The part of the bus that's responsible for keeping the satellite where it needs to be and doing all of the flight related things. And then you have the payload, and they're supposed to be entirely separate systems. Like they should have no interaction really. And so I was mostly focused on flying the bus. But a lot of that was just figuring out what did it need to do, like what were the sequencing that needs to happen, what sort of orbital maneuvers would we need to do. I learned way more about orbital mechanics than I ever had intended to ever learn. But I was only with that project for, maybe a year or so before that project got turned down. And that's around the time that Starlink got started up. And but one of the pieces that we had built or started to build out of this was, like, even though I was mostly focused on the flight control side, officially, I was working with a lot of folks that I knew from the server teams and the networking teams on, there's an interesting data routing problem. Like, how do you actually build a network that goes through multiple satellites? Because you not only have the classic networking problems like in Wi-Fi of what's my quality of my link, you now have a problem of everybody's moving. And so the potential set of links that you could form is constantly changing.
Right.
So I was working with them through that problem because it was just kind of fascinating. And we ended up building that system. And we ended up calling it the first spatiotemporal software-defined network. And it literally is. It's a cluster system that just kind of evaluates where everything is in space and evaluates all the potential RF links based upon the radios and pointing capabilities that each of them have, and comes back with solution sets so you can predict in the future where it's going to go. And that ended up following through a couple different follow-on systems of repurposing it, because we built the system to track anything. We didn't care how it was moving. So it was like, oh, we're not on satellites anymore? Well, guess what? It works on aircraft. Oh, you're not on aircraft anymore? Well, the loon folks with their balloons, they could use that too. You want to do between balloons and aircraft? Sure, why not? So that project actually continued on and eventually got spun out, and some friends of mine still run that as the company. I can't remember the name. But yeah, so that's actually a product that they're trying to sell now on the market.
Yeah. Was the so obviously, Starlink has gone on to be successful by a lot of measures presently. What was kind of some of the blockers at that point in time? Were there any technical blockers, or was it mostly organizational in terms of that project's fate within Google?
I mean, yeah, there were a lot of challenges. Not only like from a technological standpoint, there was a lot of how do you actually build LEO to ground radio comms that tolerate basically how do you build the ground station, or like the user access terminals, not the gateways. But there were a lot of challenges with just the technology for building the antennas and stuff to hit a price point. It would be trivial if I could have you spend $5,000 to buy a steerable antenna, but that's not practical for that type of system. So the idea of getting to that, panel that's actually a phased array of all sorts of antenna elements was a lot of technical development that was going on, and Starlink has definitely moved in that direction and shown to be successful in that area. There's a lot of other aspects in terms of the software backend of, not only the data routing but the flight planning. We had a lot of discussions around how do you actually keep in touch with all of the other organizations that you need to about potential collisions in space. Like, there are processes established for this, but they were never designed for the scale of the number of satellites in space. And so they don't have the ability to do that conjunction analysis that fast. So there were problems associated with that, like, lots of different things. But from a technical standpoint, a lot of it was, how do you just build the radios? How do you build the power systems? How long is the satellite even going to last before you have to intentionally deorbit it? And a lot of those turn directly back into business problems. If I have to replace a satellite every month, that's expensive.
Right.
Yeah.
So you mentioned also kind of like collaborating with the server and networking folks during that time. I'm not very familiar with the architecture of satellites, and especially internet satellites, if you will. Is it essentially like a flying server? It kind of sounds like I couldn't help but draw analogies between what you were talking about with the flight control system and the BMC that we were just talking about doing similar operational tasks for the server.
And it's not a bad parallel. The main difference is that, a flight computer has to be radiation tolerant. It has to not fail effectively.
Right.
Otherwise, your satellite's completely useless. And that's the worst case, right? Like, the absolute worst case for a satellite is you lose control of it and it's just there and you can't intentionally deorbit it. Like, if the payload fails, I can intentionally deorbit it and get it out of space, out of space, right? I can get it to burn up in the atmosphere. And that's a much better result than having it just be there as inoperable. So the flight computers and the everything related to flying the bus tended to be spec'd for much higher reliability and a much longer lifespan, so that you were pretty confident that you'd be able to fly the thing even if you lost the ability to use the payload to actually run the data comms.
I see. And I can't help but think about as well. And this, you mentioned the episode with Nathaniel earlier, and we talked about their CT scanners. And naturally, what came to mind to me was, how are you updating these systems? Partly because I work for an IoT company during the day, so we're always thinking about OTA updates and that sort of thing. What was the software update process like for these satellites?
We didn't actually get that far in terms of the development.
Okay.
I mean, it was like, try to make the system work first and figure out what all components you were going to have and then figure it out. But it was definitely a very key thing on mind of a firmware update that kills the machine is not okay, right? Like, you have to be safe no matter what happens. And so there were a lot of thoughts towards, how do I actually get the system to come up in a mode where I can use one of the radios to basically be a serial port to the console port and be able to upload things over X modem if I have to, kind of stuff.
Gotcha. So after working on that, you already mentioned the Open Compute project and your involvement there, and maybe somewhat kind of like tangential to that. I know you started getting involved in open source FPGA tooling. What was obviously, there's quite a bit of FPGA usage in data centers for things that are kind of like similar to a BMC, or where they're doing some sort of operational task. Once again, Nathaniel and I talked about that on the Oxide sled. But how did you get interested in FPGAs, and then especially get interested in the development tooling? I mean, from my perspective, it's hard not to get interested in it when you suffer through using it. But what was your path to kind of getting exposed to that?
I had used FPGAs a little bit in college, and frankly, like, with the way Google did their server designs, there wasn't much involvement. The network group tended to do a lot more with FPGAs, and I just didn't have a lot of exposure to it there. But as we got into working on BMCs and things, one of the things you find quickly in that space is there are two companies that make BMC processors. There's ASpeed and there's Nuvoton, and that's it. And part of that just comes with it's a very strange set of hardware capabilities that you're looking for. It's not about the software. Why can't you use an ST Micro for it? Well, I need like 15 I2C controllers, and I need 6 PWM controlled fans with tachometers, and I also need custom protocols that the processor vendors make up. And that's just not a thing that you find in general. And so there was always this thing of, well, the ASpeed parts are not great. They're not well designed, and the Nuvoton ones are expensive. So what if we made our own? And of course, the answer is that's ridiculous. Nobody wants to make their own chips. You can tell that was a certain time period at Google.
Right. I think there's an announcement today about some new ARM server processors at Google. So.
Right. So that's changed over time. But at the time, I had discussions with like Bart Sano, and Bart was just like, I've done chip design before. We're not doing chips. And it was like totally reasonable. So there was always somebody that was like, well, what if we used FPGAs for this? And so somehow through the open compute work and through those kinds of discussions where we kept wanting to use FPGAs to replace these BMCs, I got connected with Tim Ansel. Mm-hmm. And Tim was trying to get together a pitch to the internal startup incubator at Google to develop open source tooling for FPGAs. And I thought, you know what, this sounds really cool. Like, I understand where this problem is, and the FPGA tooling is absolutely horrific.
Right.
So sure, why not, right? Like, this is an area where I can go in and they'll give us a year to work on this and see where we get. And that was really the introduction to it. It was just I kind of understood where the problem was, and figured I could help. And they were happy to have me come join. It was only 3 of us really working on it. And a lot of it was actually not so much building the tooling as it was figuring out how to reverse engineer the chips themselves, which mm-hmm. is a very different skill set.
Right. And I think you worked on Project X-Ray, the Xilinx bitstream reverse engineering.
Yeah. So, I mean, Project X-Ray has an interesting history. Claire Wolf, who did the Project Ice Storm mm-hmm. For the Ice 40s, actually had started Project X-Ray much earlier and figured out that these are big, complicated devices, and it was going to be really hard to do. And the Ice 40 was an easier target. So this was actually picking up that work and going with it. And this was really the reason for having the project be done through the startup incubator, was to give us time to actually go figure out how to do this. And so it was 3 of us working on Project X-Ray, which was, you can think of it as coming up with arbitrary designs that probably didn't make any sense. Mm-hmm. Feeding in Verilog or specific device like placement things, and then setting really strict constraints to force very simple circuits to be placed in very specific locations on the chip, so that we could then take the resulting bit streams and compare them against various permutations and see what bits changed. And from that, infer what behavior each bit actually was doing. Mm-hmm. So you'd have to settle out, was this something where this section had always changed? Oh, that's actually the ECC over this section of the configuration ROM, or the configuration data. Or is this actually the bit that tells me use this input to this LUT kind of thing? Right. And so a lot of it was writing tools that did that analysis. And I wrote a lot of tooling for actually picking apart the multiple layers of encoding that they do for the bit stream that actually gets stored in Flash to get to the actual configuration data. And mm-hmm. We got pretty far, but it turns out Xilinx 7 series FPGAs have a lot of different tile types, and there's a lot mm-hmm. of bits in them. And it took they're still working on that project actually many years later. So it's a tall order, but it was a lot of fun.
Absolutely. So, did you also get involved in any way in kind of like some of these modern HDLs? Because obviously, you already mentioned Verilog. There's System Verilog VHDL, but it seems like also on Hacker News every week there's a new kind of like HDL that someone has done as part of their PhD thesis or something like that. Did you have any involvement in those areas? Because I know that SymbaFlow was right the name, was that the name of the whole project?
Yeah, that was a top level name for doing Project X-Ray and trying to use available open source tooling to actually build out a tool chain around it. So it was do
Okay.
the reverse engineering work and then be able to use that to build out a tool chain. And there's just this small community that actually works on this kind of stuff. And once
Hmm.
you get introduced to that community, you also find that that's where all of these modern HDL folks come from.
Right.
So that's where I met folks like White Quark, who does the Amaranth, and
Right.
a lot of those folks I got introduced through that path of, hey, I'm working on Project X-Ray and getting into IRC chat rooms and talking about the tool chains and what's going on. And so I know some of the folks that do some of them. And I keep track of it because ultimately, when you approach it as like a compiler problem or a software engineering problem, the Verilog's a terrible language.
Right.
And System Verilog is the C++ of HDLs, and
Right.
they're useful, but they give you a lot of foot guns.
Hmm.
And the modern HDLs, some of them do better at some areas than others, and they all have their different trade-offs. And I think it's really just a renaissance of trying to come up with an HDL that better represents the problem at hand. But there's kind of this fundamental challenge that happens there too of, because the tooling is kind of nascent in the open source space, like Yosis works, but has its limitations, and NextPNR has its limitations, then everybody falls on well, if my modern HDL generates Verilog, then I can feed it into
Right.
the vendor tool chain. And it's kind of like the JavaScript situation.
Hmm.
You have TypeScript, but TypeScript really just compiles down to JavaScript anyway.
Right. So you worked on that for a year, and then that was kind of when you started to wrap up your time at Google, right?
hmm Yeah, I mean, the way that the startup incubator worked, it was you do your work for a year and then you come in for a review and then you do a review every 6 months to get renewed or not. And just after doing that first year, we did a lot of work, but I was having difficulty seeing how the project would succeed with what the goals were being outlined, and where to go with it from a big business perspective. And having spent 9 years at Google at that point, like I had watched the company grow in a lot of different ways and kind of change culturally, and just decided it was kind of time for me to move on to something smaller. Uh, as you may have gathered, I at this point had worked at two extremely large companies,
Right.
and just had an opportunity finally where I could actually go work at a startup. Like I'm at a point in my career where that works okay, and so I started just shopping around for what was out there. And we didn't really touch on it but while I was working on server designs and things, I got heavily involved into hardware and firmware security aspects, and more into PC security in general. And so I ended up, finding some startups that were working in that space and moving over that way.
What kind of drew you into the security realm? Was it just like once you start understanding a system really deeply, you kind of have this natural kind of thinking about, oh, I wonder how this fails, or I wonder where the holes are in this. Was that kind of the impetus for you?
I always had the aspect of looking at it from, how are things going to fail? Because that's what health monitoring and like, automated diagnostics is.
Hmm.
And but there's a slightly different angle when you start looking at how operating as a public cloud vendor works. And that was really there were two big shifts that happened while I was at Google. One was the Aurora attacks, which is a well documented like campaign against many different companies by um, threat actors that uh, are believed to be associated with the nation, um, and that affected, like, they were targeting my team. It was one of their targets, right? So they
Hmm.
were trying to figure out how you could do persistence by getting access to firmware and building backdoors and things into firmware. And so that just kind of spooked things in a lot of ways, and really caused a lot of rapid changes to how we developed software and firmware and how we deployed things to production, et cetera. So I got a lot of front experience too. Like, we were a pretty free and open how you do all this, and then a very closing it down. But then as Google became a public cloud provider, there was another thing of, well, now I'm running untrusted code. And so how do I actually provide isolation? How do I do all these different things? And I was not actually working on that, those set of problems, but I was working on the hardware they were running on. And so we'd get these questions of, well, how do you bootstrap from nothing? And how do you know that it's trusted? And it mostly tied into, manufacturing operations. How do I know that when I receive a server from the manufacturer at the data center door that it wasn't tampered with at some point? And we knew that we were a big enough target that we had to pay attention to all of these cases that a lot of folks just don't, right? Like, when you buy a laptop, you probably assume that you're not interesting enough for a three-letter agency to intercept it and do something to it before it arrives at your door. But when you're Googled, you don't get to do that, right? You have to think through some of those cases and how would you actually find it. So that's a lot of where my introduction came into it, and working on some of the things. Like, I worked on how Titan was used as the root of trust and measurement in the systems and the server designs, and I co-wrote one of the white papers on how that system works. And so I had a basis there from that perspective, but then I ended up joining a startup that was much more focused on application security, like how do you defend against people sending malicious attacks to your application running on a server, which was just a very different field for me, but it was also at a startup where I was working with like 10 people. So it was trying something different.
Right. So talking a little bit about the Titan system that you were mentioning there, can you talk a little bit about how that system works, and maybe some of the strategies you'll have at the hardware/firmware level for mitigating some of these attacks?
Yeah, I mean, a lot of folks often think about UEFI Secure Boot or Intel Boot Guard as this way of defending sort of what we ended up calling the first instruction integrity. When I press the power button, how do I know that the first instruction that the CPU executes is actually trustworthy? Because once that instruction executes, I have no control over. Like, if I can't trust that first instruction, I can't trust the second instruction either.
Right.
And it's a very difficult problem, actually, because the PC architecture has grown over time, and this was never a concern in the early days. So all of your firmware is stored on a flash chip that is outside of the chipset. It's on the motherboard for sure, but if you have to consider somebody coming through and having physical access to a machine, they could change the contents of that. Or if you have an attacker who managed to gain access where they could write to that, then how would you know? How do you detect tampering? And frankly, a lot of the question is not so much about defending. It's not prevention. Usually, that's certainly a goal, but the assumption is that someone's going to get through. And so the question becomes, how do you detect and how do you mitigate, or remediate? And so that's a lot of what the Titan design was about. It was, how do I do opportunistic prevention of someone writing to the firmware, but also if someone managed to get something in, how would I actually be able to power down the system, power it back up, and know that I had gotten full control of the system back, and that I didn't have some tampering in, the system firmware somewhere. So in that design, it's actually an interposer on SPI. So essentially, it sits between the processor, the host processor, and the SPI flash, and watches and actually, it does more than watch. It actually intercepts all of the traffic, all the read and write requests over the SPI interface for the contents of your firmware, and makes a decision about whether or not it should actually pass it to the flash and whether or not it should get the contents back to the host system. So it essentially gets to make decisions about, are you allowed to write to flash? And it also does cryptographic verification. So when you write to the device, it actually is building up a hash of the firmware and then validating that matches a signature before it will ever allow the write to actually complete. And so by acting as this intermediary and also having control over the system reset line, when you power on the system, it actually does a hash over the contents of the flash, and then it verifies the signature chain, and only then does it actually let the system boot. So you get to a level where attacking the system requires much more physical access. You can't, it's not as simple as, oh, I get root access to the machine, now I can just write to the flash. Nope, it's not going to let you, and there's nothing you can really do about it other than physically get hands on it. And even if you do, even if you physically change the contents of the SPI flash, it's still going to notice that you did that.
Right. So you'd have to actually physically manipulate the Titan component, right, to
Right.
actually make any headway there.
Right. And of course, there's a lot of technical limitations about this. SPI is very fast. I mean, it's usually only like 33 or 66 megahertz, which doesn't seem particularly fast. But the way the protocol works, when there is a read command, you have 2 cycles before you actually have to send data.
Mm-hmm.
So you have very limited time to make any decision or do anything. So there's a lot of small things there of getting that system to work, and it's really a bolt-on solution. It's not great, and this is why you see other systems like TPMs are another system that Google didn't use up to that point. I don't know if they do currently or not, but it's another bolt-on system, right? It's another way of adding something to the PC infrastructure without radically changing how the system works to kind of add additional security properties to the system. And you see that kind of trend over time, that it's, how do I take the PC and add something to it to give me a little bit more guarantee about how it works?
Gotcha. So as you moved into some of these security-focused startups, I think you had kind of more of like a researcher role, perhaps, than you previously had been more of an engineer. Was there a practical distinction between those two, and what were the differences, if so?
There was. I mean, certainly as I moved into working at Eclipsium, which is much more focused on firmware, there was a need for someone who actually understood the system infrastructure and could do research work of how could I break the system, right? Like, how do I get ahead of attackers and the things that they could find, what vulnerabilities they could find. But there was also a need for somebody who understood that and could translate it into how you would build defenses for it, right? So like you'll hear security folks talk about red team, blue team, and now there's purple teaming because why not have both? And red teaming is figuring out the attacks, right? It's offensive, trying to figure out how to break systems, and blue team is how you defend. And so they needed someone who spanned those two teams. So I depending on the day, it was sitting down and writing in their application how to detect whether a system was configured in a way that would allow for certain vulnerabilities, right? Like looking at chipset registers, looking at flash configuration, et cetera, and reporting on that information so that you can make decisions about the risk of your fleet of machines. But there were other days where it was, hey, I've got this machine, let's go see what we can break on it, right? Like that's...
Right.
Yeah.
And what was it mostly, vendors or companies that were, running data center scale compute that would hire Eclipsium to come in and kind of like do this analysis? Or what was kind of what's the business model for that type of business?
I mean, the business model for the product is more, selling to companies that have large deployments of machines as kind of a monitoring system, right? Think of it as like an endpoint, like your antivirus deployments, right? Except it's something that's scanning your machines, looking to see, do you have systems that have out of date firmware that have known vulnerabilities, that kind of information. But the research side was more keeping the interest in that. A lot of folks just assume that their attacks are going to be more application focused or operating system focused, and they just don't even need to think about hardware. That, I bought my equipment from HP. It's HP's problem. And so a lot of it was, how do we keep finding new things to point out that the vendors aren't actually doing this work, right? They're building the machines, but they're not actually thinking through the security problems. And occasionally we would have a vendor who said, we did something cool. We want you to actually look at it and see if you can break it. But that was very rare. Most of the time it was just, hey, we bought this thing off eBay. Let's go see what we can find. And you'd be amazed at the stuff that was found. I mean, sometimes you just buy something off eBay because it looks strange, and it turns out it's already, it was a vehicle mounted unit or a computer that has a cellular modem and still is registered with FedEx's Active Directory domain. It's just too easy. And other times
Right.
it was, we bought this server and we started poking around and we were just like, it looked like maybe there was something that you could do over here, and we'll just keep poking at it. And then you find, oh, I can do a authentication bypass on the BMC, and now I have total ownership of the system, things like that. So the
Yeah.
business model was kind of keeping pressure on the vendors to do better and use that to raise awareness so that people thought about buying the solution of having a way to know what vulnerabilities were in there and how to do remediation.
Gotcha. That makes a lot of sense. So kind of like talking to BMC vulnerabilities. One large thing you were a part of, or kind of discovered while at Eclipsium, was this USB Anywhere vulnerability, and you've given some talks on it, and we can certainly link those in the show notes, as well as the report itself. But do you kind of want to run through what USB Anywhere is, and also how you went about discovering it?
Yeah, USB Anywhere is a vulnerability related to BMC virtual media. So we kind of mentioned this earlier. BMCs offer this lights out management capability, and one of those things is I don't want to have to walk into the data center to stick a CD into a machine to reinstall the operating system or to update the device drivers or whatever. So instead, it has the capability for, from your web browser, mounting a CD image as a virtual CD-ROM drive on the server somewhere else. And I was always just curious how that actually worked, is really how it started. I knew from my work on OpenBMC that the hardware level was a dedicated piece of hardware that emulates a USB device. So you see this in mobile phones. This is kind of how like USB to go works, where if you plug in a USB, or when you plug your phone into your computer and it's like, here, you want to download your photos, like the phone chip actually has the same kind of hardware where it can emulate any USB device. Like it's a USB endpoint that doesn't have a fixed device to it. It's not one specific thing. So you write software to implement what it does, how it responds to requests. And so I knew that existed in the BMCs, and that the firmware was actually deciding what level of, or like what kind of devices it was. That's how your keyboard emulation works, how your mouse emulation works, how your, a lot of different things. But the virtual media, I was like, how is this getting from my browser all the way there? Mm-hmm. Because it doesn't seem like it was transferring the entire file over before starting it. And so it turns out that it's a horribly insecure protocol. What actually is happening is that in older BMCs, they would ship a Java application to you. On newer ones, they do it via HTML5, which is kind of even worse in some ways. But essentially, like in the HTML5 version, there is a JavaScript library running that in your browser that is an entire SCSI stack. And it is actually, and an ISO file parser. And so it's actually JavaScript running in your browser, opens the file in your local machine and presents that as a block device to a virtual SCSI device that knows how to answer SCSI requests like it is a virtual CD-ROM drive. And that is connected over a WebSocket to the BMC. And then the BMC is effectively just forwarding the request back and forth. It's actually speaking raw USB requests over that. It happens to be sending USB mass storage, but it's actually just sending raw USB packets. Mm-hmm. So, this is always comes as my example for when folks are like, how bad can it be for, they're like, I've seen the worst thing in programming. I'm like, have you ever seen a SCSI implementation in JavaScript? And so the Java version is very similar. It happens to be written in Java with a JNI extension, but it's the same basic problem. And it turns out that, they had just built their own thing. The vendor had a long time ago and had not really updated it. And the way the ecosystem works around BMCs, there's a couple of key companies that make the hardware, Nuvoton and ASpeed, and then there's a couple of key companies that make the operating systems for it, so like AMI and Vertiv and a couple of others. And then the companies that actually manufacture your motherboards just license both of those, or like they buy the chips and they license the OS, and they do a little bit of customization to it. And then that is sold to whoever puts the name on the box, and then that's what gets sent to you. And so fixing bugs is a complicated process. And so oftentimes the same bugs show up again, or they just never fix it because it's hard to get the communication across all these teams and companies. So in this case, it was doing things like it was unauthenticated. If you did authenticate, it was trying to use encryption, but it was a very, very, very old encryption that was trivial to break. It had hard-coded passwords in it. It had, just all sorts of things. And so my proof of concept for this initially was using a framework called FaceDancer that lets you develop virtual USB devices in Python. And I wrote a backend that connected it so it would actually connect to the virtual media service on the BMC. And the very first time I got it working, FaceDancer's default is to emulate a TI calculator. And so I logged into the server and I do LSUSB and it says that there's a TI 83 Plus connected. I'm like, I don't think that's right.
Right.
But yeah, I ended up doing a demo where I actually plugged in a virtual USB stick across the internet over to a server many states away, and it was actually just a file on my drive locally. And this is kind of terrifying because this was unauthenticated access. So you could literally, if you could find a way to talk to one of these BMCs, you could plug in any USB device you wanted, which seems like not a big deal until you think about it a little bit more and you're like, oh, that's actually terrifying.
Right. Wow. So what was the reception like when you put this out? Was there, obviously we've had recently some vulnerability discoveries that caused some hysteria, I would say. Was there a lot of feedback when you put this out there?
On one hand, there was a lot of folks that showed up that said, oh, you figured this out too?
Yeah.
Right? This was just sort of an open secret that BMCs... I actually had someone write to me and say that finding vulnerabilities in BMCs was unsportsmanlike. So, I mean, there was that sort of reception. And then on the other hand, there were a lot of folks who just had no idea that this functionality existed in the first place. Mm-hmm. And then to see that you could abuse it in this way was absolutely terrifying. So I did end up getting some national press and things for it, but it really didn't have a huge... I mean, I did some talks on it, but it didn't cause the fervor that some of the more recent vulnerabilities that show up on literally everyone. And part of that was just that most people try not to put their BMCs on the internet. It turned out that as part of this, I have a friend who happens to run an internet exchange. And so he let me have a VM and I ran a scan of the entire internet for affected BMCs and came back. And so, part of the story was actually that I found, 30,000 plus BMCs that I could just arbitrarily plug USB devices into.
Right. Because, I mean, obviously the USB part is bad, but you have to have access to it, right? So it being on the network is kind of the prereq. And, how does that happen?
A lot of people just don't know. I mean, they're like, oh, I got this cool feature from the vendor that says I can do remote management. Let me just plug that in so I can do it from home. Right? Not thinking about the vulnerabilities that it might have or anything else. And so there's just,
I see.
How do you actually do the risk assessment of equipment that you're buying? And that's a perennial problem. There doesn't seem to be a good answer to that.
Right. So kind of bringing the security and your previous server work together, from Eclipsium, you went to Oxide, which listeners of the show will be familiar with at this point after the last episode. What was kind of the decision like to join Oxide, and what was the kind of role of looking into security there? And I know you and I believe your colleague Laura Abbott also identified some not similar vulnerabilities, but vulnerabilities at similar layers of the stack there.
Hmm.
Yeah, what was the decision like to join Oxide, and what kind of work did you do there?
Yeah. So I had been at Eclipsium for a while and kind of had the viewpoint of it was fun finding vulnerabilities and reporting them. Getting vendors to fix them was hard, and actually building the detections for some of these things was also difficult, and it just wasn't a good fit for me anymore. Like I needed something a little bit more concrete. I like building tools. I like building systems and stuff like that. And so I had gotten in touch with Jesse Frizzelli about BMCs and that kind of stuff as some of the discussion was happening around starting Oxide, and ended up meeting Brian and had some good discussions with them. I had while I was doing all the work at Open Compute, one of the things that stuck out with me while I was still at Google was folks coming up and saying, "Hey, will you just sell us your machines? And we don't want just the machine; we actually want a software stack that goes with it, right? Like you already know how to run all this stuff. We just want to buy it and use it." And you would think this is small companies or something that were asking this. No, no, no. These were folks who were at the scale where they were buying hundreds to thousands of racks
Mm.
of machines from HP or Dell on monthly, right? Like they were at the scale where they were starting to question whether they should actually be designing their own machines or not. And so they were looking for a solution, and they were looking at Open Compute as how do I get cheaper, but I need a more complete system. And so this had been in front of mind, and I had actually tried to work internally at Google for how could we improve this? How could we um, provide these a more complete software and firmware stack for these machines so that people can actually buy them and use them. And it wasn't very receptive at Google. Google's position was basically we're designing machines for ourselves and we're sharing with the industry so that we don't have to keep doing the new development work all on our own, and that it actually gets picked up by other companies. So when Brian and Jesse came around and they were talking about, hey, let's do this thing. I'm like, I know exactly how to do this. Like, I know that there's a market for this. I've been talking with folks for years about this. I know what a lot of the problems are, and I know how to build systems like this. So I initially told them, I want to work for you folks, but I don't think you're going to get funding because I don't think you're going to be able to convince anyone, any VC that you're going to fund you for long enough to actually build the system that somebody would buy.
Right.
Um, and they succeeded, right? They had got their seed round, and it was enough. And it was on terms that this is going to take years to build,
Hmm.
and that's okay. So at that point, I was like, all right, I'm in. I came in not really focused specifically on security. I certainly brought that background, but it was definitely just let's build this the right way, right? What would Open Compute look like if you were actually trying to build it as a sold product as opposed to a repository of standards and like prototypes for other people to draw their technology ideas from? Um, and yeah, I mean, I spent a lot of work. Like I worked on all sorts of different pieces of the stack there because I wasn't particularly focused on anything, any one piece of the system. I
Hmm.
definitely had a significant security role there over time, like looking at how to build the root of trust and measurement, how to do firmware signing, how to, build out a system where at power on you can trust the system in much the same way that Google was designing their systems to do the same thing.
Hmm.
Um, but I also worked on fan control, and I worked on, how do you do the lights out management features, and how do you actually power up the 100 gig network cards, and all sorts of different things.
Right. And so you'd had this kind of experience with BMCs made by two vendors that were not necessarily great. When you had the opportunity to do it the right way, what was the right way?
Well, I don't know that there's any right way necessarily, but there was definitely, if I don't have to play in the sandbox of building a PC compatible system, if I'm
Hmm.
not assuming that I'm just going to boot an off the shelf operating system with no work, then I can throw out a lot of things. And if I can do that, then I don't need these specialized chips. I can build it out of commodity chips, which, by the way, Nuvoton and ASP didn't really want to sell to me anyway, because like we're a startup, they don't want to
Right.
sell to us.
Right.
um, So, uh, just looking at it of how do we build this out in a way that meets the needs? And it turned out like one of the things is that BMCs were starting to become seen as a way of building your root of trust measurement. So
Mm.
the repository of information about what was booted on the system. And that's kind of scary because the BMC also is a network accessible device. And that's just sort of like feels wrong.
Right.
I don't want my secure element to also be network accessible necessarily. That's odd. So a lot of it was just trying to pick apart what sort of functionality do we actually need? Do I actually
Hmm.
need a graphical console to the machine? And the answer is no, right? Like Oxide's thesis is you don't actually need to know any of the details of the machine. That's not what you're buying. You're buying a rack. And the rack has the interface. The notion that the machine, each individual machine is booting an operating system and has management controllers is an internal detail that can be hidden from you. And or not necessarily like we're trying to intentionally hide the information, just like you need the output of that information, not all the details of how it worked. And you don't need to write the software to deal with that problem. That's my job. And so being able to split that up into multiple microcontrollers and design the system to have all the features that we always wanted. It's there's a lot of Nathaniel mentioned the ignition system where it's like you can actually control the machines even if they're powered off, even if 90% of the board is dead. Like you can control the main power control to each tray, and that was a decision that we made, a design choice that we made of having that level of control of the system as a way of being able to recover from various scenarios. Oh, the machine's locked up and the service processor crashed. I can actually hit the reset even harder. That's
Right. Right. So you mentioned having kind of like multiple microcontrollers playing the role that the BMC traditionally would.
mm-hmm.
So you have the service processor. Is that doing kind of like the bulk of the BMC related management, and what other microcontrollers or FPGAs and other chips are kind of involved in kind of like providing a chorus of components that are playing the role of the BMC?
So Ignition is its own dedicated FPGA that just does this lowest level of being able to turn the power on and tell you if the initial power stage is functioning. And so that was designed to be as simple as possible. It should never fail. That was the goal. And so that becomes its own dedicated thing. Then the service processor, yeah, that's the bulk of the functionality. It's doing the fan control, it's monitoring the power rails, it's doing a lot of different things, inventory of the system, etc. And then the other main piece of it is the actual root of trust. So root of trust measurement is very similar in concept to what Titan actually was doing in the Google design, but a little bit more integrated because we could, and build on commodity hardware because we could. Which that took a lot of time. It took a lot of time to find a device that we were very keen on not having to sign NDAs on to get the documentation for these parts. Like you can go to vendors and get details on actual secure elements, but they are heavily restricted on just getting the documentation on it. Like even getting a brochure on which parts are available is a restricted document. Where we were looking at parts that, yes, there are some aspects of them that are under an NDA, but generally you just had to maybe create an account to download the bulk of the documentation. And the intent was that we were going to open source all the firmware anyway. So we wanted you to be able to have not only the firmware, but also the ability to actually go comprehend what it's doing. You should be able to read the data sheets.
Mm-hmm.
So
And
the root of
so,
trust, got built off of another commodity part. It happened to be one of NXP's LPC 55 series parts for a variety of reasons. Like I had a very long and detailed document around how we did the assessment of which device, like selecting which device based upon its security properties. And that was the whole point. This was a device to manage the root of trust and do key management. It was very dedicated to that purpose.
And compared to some of the other options, it likely was had some security capabilities that were preferable, but you also discovered that there were some issues. What was the process like for identifying? I think there's 2 vulnerabilities that y'all ended up discovering. Is that right?
Yeah. Honestly, we weren't specifically looking for either one. We were looking through the chips as how they worked and the potential for vulnerabilities, and everything from I sent it off to a friend of mine who does decapping and like being able to look at it and see, does this have a security mesh on it? Does it just that high level type things. But there were definitely some features available in the chip, like it has a physically unclonable function, which is basically it's an SRAM cell, it's a memory cell that intentionally you can't write to. You can only read from it. And so it comes up in an uninitialized state. But because of the silicon processing, the state is unique to the particular section of wafer that it was cut out of. So you can apply a probability weighting to it and get a consistent readout. So you can say, like, every time I power on, I apply this matrix, probability to each bit of the SRAM readout, and that gives me a way to generate a unique identifier for this device. And since it's based upon the actual silicon properties, you can't copy it. And so that was a cool piece, right? Like we used that actually. But as far as like the vulnerabilities, we weren't digging really that far into it. We were actually just trying to figure out how to use the device. A lot of microcontrollers nowadays have a built-in ROM that does their initial bootstrapping, offers some of the common library functions or power management type things. Instead of you compiling in their code as a library, it's just you call this section of the ROM. And we were just trying to understand how the code signing system worked initially. And we were generating a variety of different binaries that we wrote with the different headers, and we're signing with the different key types and things, and just encountered unusual behavior. We started reverse engineering the ROM just because we needed to understand how it worked, because the documentation didn't tell you. And NXP wasn't really particularly forthcoming about how it worked. They just wanted you to use their tools, and their tools were insufficient for our process. So we had to dig deeper into it. But once, the chat room sort of like, hey, can somebody look at this? This is odd. Followed by, a lot of active discussion around, well, what is going on here? And then, oh no. Oh no. And that really happened for both of them. We were looking for something else entirely. Trying to just understand how the part worked and realize that you could manipulate it in ways that bypassed various countermeasures or, caused the chip to do things that it's not supposed to do. And then having come from the world of working like at Eclipsium and doing vulnerability disclosures, it was like, okay, I have a process for this. I know how to do this. So here's how we talk to everybody. Here's how we coordinate it. And honestly, the talk that Laura and I did at DEF CON was entirely driven by spite. The vendor's response was so poor and so frustrating that I submitted the talk to their call for proposals, and didn't expect to get accepted, but we did, so we had fun.
That's awesome. How did y'all go about actually dumping the ROM and then analyzing the code that you got off of there?
So on those parts, it's actually the ROM is intended to be readable, so it's actually just really trivial if you just write a program that goes and reads it, or use a debugger to dump it. It's just accessible space. Other chips I've worked on, you have to do clever tricks. You have to find a vulnerability itself to get access to it or something.
Right.
But then once we had it, it's mostly loading it up in Ghidra and spending a lot of time. Reverse engineering is a skill. It's a lot of people see it as this very difficult task, and in a lot of ways it is. But it's really a puzzle problem. It's finding patterns and recognizing things and building up an understanding of how things work from small levels to bigger understanding. And so we just had a couple folks that we would share it around, and we all had Ghidra, and we would just pull up different sections of it and start working through, oh, this is a mem copy. Oh, this is a strlen. Oh, this lines up with these registers that the datasheet says. And then you could start to infer what the behavior was. From the breadcrumbs that I had, you could trace what it was actually doing. And the ROM was small enough that you could mostly get through it and understand it. Whereas on some other devices I've worked on or other software, once you have like a megabyte of code, it's just, you can't realistically reverse engineer the whole thing.
Right. Makes sense. Well, after Oxide, you went in and we're 90 plus minutes in to the conversation now. But I'm going to ask you to explain quantum computing now. So you went on and you joined IonQ. And I have spent the bulk of my research for this episode on quantum computing because I'm coming in with very little experience. I do have one friend who is doing a PhD in quantum error correction, so I'm familiar with some of the constraints of of quantum computing. But for the listeners and for me, talk about your decision to join IonQ, but also can you give us kind of a bit of a primer on quantum computing?
Sure. So I was looking for a place to work. I had moved to the Seattle area while I was working at Oxide, and for reasons I was just looking for something in this area, and I honestly applied to be director of security at the company. And in the interviews, they said, oh, well, we're not actually hiring for that role right now. We've decided we're not going to hire anyone for that role. But your background is fascinating, and we would just like you to interview with some other folks about this embedded control systems. I'm like, sure, I know absolutely nothing about quantum computers, but I just assume that like you're going to have physical hardware and I'm going to understand the security properties of this and we'll figure it out.
Right.
And between all of the work that we've talked about, processor design and health monitoring aspects and flight control systems and all these different pieces, it's just like, yeah, I've worked on embedded real-time control systems sometimes, and I have some understanding there. So I really came in knowing nothing and not expecting to end up in this team. As for how quantum computing works, I always get asked this question after like an hour of discussion, and it's great.
Right.
So here's the capsule summary. Quantum computing, there's actually a really great tutorial on this online. I think I sent this to you, quantum.country, that kind of walks you through thinking about how quantum computers work from a programming centric or like algorithm centric model, and it kind of walks you through the basics. But the top level idea is that a quantum computer is something that can represent or do computation of quantum mechanics more efficiently than a classical computer. The practical aspects are that you're really dealing with this model where somehow you have a thing called a qubit. And we call it a qubit because it's quantum, and it's not actually a bit. It doesn't have just a 0 or a 1 state. It's a probability function. And often what people express it as is what they call the Bloch sphere, where imagine you have a sphere, and the north pole of the sphere is the 0 basis state, and the south pole is the 1 basis state, or vice versa. It doesn't actually matter. There is common nomenclature for it, but I don't remember what it is. The idea with the Bloch sphere is that it's a unit sphere. So you've got the two poles defined as known states, and then every other point on the surface is somewhere a unit vector based upon like spherical coordinates, right? Mm-hmm. And wherever you are on the surface defines a probability that if I measure that qubit when you're at that position, the closer, whichever pole you're closest to, you have a higher probability of going to it. So if you're at the equator, you have a 50-50 chance of going to either side. But if I'm, a quarter of the way up the north, then I'm like 75% chance of going to the north. So I would be a 0, right? Mm-hmm. So the output of a qubit is always either a 0 or a 1, but it's a probability. And so quantum computing is mostly around doing operations to move the point around the unit sphere, such that when you measure it, you get some result that collapses to a 0 or a 1. And an interesting part about quantum computation is when you do the measurement, you destroy all of the other information about where exactly you were on the sphere. You only know the output of a 0 or a 1. You don't know anything else. But while you're doing the computation, you actually can control very finely where you are in terms of spherical coordinates. You can do sort of arbitrary rotations around the sphere. So that's the computational basis of how this kind of works. And how the algorithms work and other stuff is a whole separate discussion around quantum computing theory. And the quantum computing practice is more of what I deal with, how the machine works. And to that end, quantum computers are kind of at the state that classical computing was in maybe the 40s, where there's a theory of how quantum computing works. There's a couple of specific use cases that show promise for why you might use it. But nobody's really knows how to build a good one yet. And you're trying to figure out the raw technologies that actually make it work. So like with classical computing, there were people doing relay computers, there were people doing vacuum tubes, there were people doing all sorts of things, right? And for data storage, we had Williams tubes and mercury delay lines and all sorts of different things, right? Because we just didn't know how. Well, quantum computing is kind of the same way. We know that you can build quantum computers out of transmons and out of trapped ions and out of superconducting systems and all sorts of things, but we don't really know which one of these is going to be a good way of doing it. And so everybody's going in different directions. And similarly, there's no coherent or consistent programming model, I guess would be the right word, around what the correct set of operations would be. We don't know that incrementing 1 makes sense as an operation, where that makes obvious sense in a binary world. It took a while to figure out that using binary was the right answer, and that when you had binary, you should use 2's complement to express the numbers and all those things. We're still figuring that out in the quantum world. So with IonQ, I work primarily, they exclusively worked on trapped ion quantum computers, which the idea is that you take a material, the systems that IonQ produces use ytterbium, and basically you use a laser to ablate a ytterbium target to cause a plume of ions to happen in a cryostat chamber that's under vacuum. And you then, that causes this plume, which gets it up into what they call the loading chamber of the trap. And the trap is effectively a series of electrodes kind of made in a line. So, and you've got this series of electrodes that constrain the ions using both RF and DC voltages to hold it in X, Y, and Z coordinate space. And so you're literally using an RF pattern as well as DC to force this ion to sit kind of in space and then be able to move it along in a line. And you do this so that you can hold the ion in very specific places so you can hit it with lasers. And the reason you do that is, if you remember your chemistry from college or high school, remember how atoms have, S shells and P shells and D shells and all these things where your electron states and your energy levels? Yeah, that's what we're playing with. Right. We're holding that ion there, and it's an ion, so it has extra electrons. And we're using laser pulses to essentially inject and remove energy to cause that electron to move between different portions of, or to different energy states. And the reason we do that is we can encode quantum information that way. And then when you get to the measurement aspect, it's using lasers where in a different sequence, you hit it with a laser and it either generates a photon or it does not. So that's how you do the collapsing onto binary 0 or 1. So the whole
I see.
system that I work on is basically a very complicated real-time system controlling lasers very precisely to aim and fire waveforms, like modulation of lasers at individual ions, to be able to then cause them to emit photons that we then have photomultiplier tubes that we actually count how many photons come out to figure out what the probability distribution was.
Gotcha. Well, I probably shouldn't say gotcha because like I'm sure that there's a tremendous information loss that just happened over our internet connection here. But the the part that I guess like I want to like press in on a little bit. So I will give a plug to IonQ's resources page here because the like background and glossary section is extremely useful. So in this kind of like period, I kind of think of it, and this may be a faulty mental model here, so feel free to correct this. But when I was learning, I started in kind of like a software background, and then when I was learning about hardware and kind of like working with FPGAs and stuff like that, you have this kind of like settle time for whatever logic you're trying to represent in your sequence of circuits. And you get there's kind of like this time, and everything reaches its steady state, and then you get the output out of it. And so when we're talking about quantum computing, and you're saying this kind of like collapses down to the photon or the mapping onto 1 or 0, the compute that happens. Compute. I'm doing air quotes for anyone on the podcast. The compute that happens in that interim, though, is happening at a like non-binary fashion, right? So I'm gonna use terms incorrectly here. I'm just gonna go ahead and put up front. And the process of kind of like when you're talking about moving the point kind of around the sphere there, is that what we refer to as an entanglement, or is that when you're taking like two of these okay, so this is at a higher level, right? Because when you're talking about the sphere, you're talking about a single qubit from a logical level, right? And
Correct.
then entanglement would be when you're taking two of those qubits and they are influencing each other in a somewhat deterministic way. Is that correct?
Yeah. So, I mean, there's a couple different things there. So, one, when we're talking about this single qubit and like that sphere model and moving around the point, that's usually what we talk about as a 1Q gate, right? It's a
Okay.
often when describing quantum electronic or quantum computation, they use a circuit model. And so you think of it like an electrical circuit, except it's not. It's like a timeline where you have the qubit going from the left to the right, and you apply gates in sequence. And so it's like something goes into a gate and it comes out the gate, but it's actually the same qubit. It's just a timeline of when you did operations on it.
Okay.
A little confusing, but you can kind of think of it like you're drawing a schematic. It's just a schematic that can only go left to right. And so a 1Q gate only works on one qubit. You have, it's an operation that you do on a qubit, and it changes just that qubit by itself. It has no influence on others. And that's doing some transformation. It's moving that point around. And the reason we talk about it as gates is there's just different operations you can do. There's like a gate that can move an arbitrary amount, you can move pi rotation, pi radian rotation around any axis. Right? That's an operation you can do. And you can do like pi divided by 2, so like a quarter turn rotation around any axis. And so those become gates. And so there's like a native gate set that the machine actually can do, and then there are sort of standardized gate sets that are how algorithms are developed. And so just like we have in a computer, you might write in a higher level language and you compile it down to the native instruction set of the machine. Same thing happens in quantum. It's just you have a standardized gate set, and then you have the native gate set, and there's a compilation process that happens. With the 1Q gates, it really is just moving around that point around one qubit. Entanglement is, as you said, when you actually cause a coupling between two qubits. You're actually like creating a situation where you're actually changing both of them at the same time in a way that causes them to have a corresponding effect later. You're mixing the the quantum information between these two. And from a physics perspective, it literally is doing a phase coherent laser modulation on those two simultaneously, which is what makes my job really, really hard. Is I have to do basically instruction level parallelism of firing waveforms at 2 qubits simultaneously, or at 2 ions simultaneously. And so that creates the entanglement there, and that's also used to do things like teleportation, which is actually a real thing in quantum. Yeah, I mean that's kind of the level of the operations. It's usually 1Q or 2Q gates. There are higher Q, like 3 or 4, but most of the time, most of the systems work on either a 1 or a 2Q gate, and it's usually a combination of the two. You run a couple 1Q, and then you do a 2Q, and then whatever. Yeah, that's what makes the control system so difficult. Is like you're actually having to sequence all of that, and then the whole thing is just to add a little bit more complexity to it.
Please do.
Even when you're not actively running a gate, when you're not actually modulating it, the electron has spin. So there is a phase precession happening just because time is passing.
I see.
And that is unique per qubit. So each qubit is actually has a phase precession that's happening at a different rate. And in order to get your entanglement to work correctly, you have to actually introduce your operations in a phase coherent manner with the phase precession of the device of each qubit. So you're actually having to track the phase of the laser pulses and make your modulation match in phase.
Right. So there's no like determinism to it. You're just measuring it and then factoring that into your subsequent operations.
Measuring it would be great, but if I measure it, I destroy state. So no, I'm actually predicting what the phase precession is going to be, and having, just based on how much time has passed.
Okay. Makes sense.
Yeah.
Somewhat.
Essentially, you're right. You run a calibration process to figure out what the phase precession for each qubit is. And you do that in a way where you destroy the state, but that's valid as long as the qubit is valid. Right?
I see. So moving back up to like sort of the hardware software interface, if you will, for these machines, right? Because I'm kind of envisioning, you're working on the embedded controllers that you have are kind of like the microcode of this machine that we're going to have instructions for, perhaps, and you need to have some sort of instruction set, right? So you talked about this model of circuits that are used to program a quantum computer. What does an instruction set look like? And I assume that due to the wide variety in implementations of quantum computing, that it's fairly varied across these machines.
It is. In a lot of ways, it's similar to how the GPU world works. Right? Every GPU has its own native instruction set that they don't tell you what it is. What they do is they give you software stack that compiles from standardized shader libraries or GPU frameworks down to that instruction set. And that's kind of where we are today, and that's probably the model that will continue for quantum stuff. But like, what does the instruction set actually look like? Well, you do express it at a high level as sort of these standardized gates, and then it gets compiled down to the native gate set. But it's still done as a circuit, right? It's like this time precession circuit model. But that's not what the machine executes. As we just talked about, it's like tracking phase coherent laser modulations, among other things, right? We also have to aim the lasers, and so there's a whole separate series of things going on there to steer them, along with dozens of other things, because we can also move the ions around if we need to. We can change their locations. So the control to the machine, the native instruction set of the machine, is actually this much more low level, but it needs to be incredibly time consistent, right? Like, we actually have to have all of these operations happen as simultaneous as we possibly can in a phase coherent way. So like, this is how this system works. It's actually pretty common in the trapped ion world, and actually somewhat common in the superconducting world. If you have this same problem, you can effectively think of it as you have a whole bunch of arbitrary waveform generators. And those are going off and being connected as to control a variety of different types of devices, but you basically just have arbitrary waveform generators. You hook them to a common clock so that they are all locked to the same reference, so they are now phase coherent. And then you are running programs where each instruction, each one of these waveform generators is getting its own instruction stream. So they're all running independent programs, but they're running off of the same clock tick. So they're executing the next instructions simultaneously across all of them.
That does map pretty well onto like the GPU kernel kind of model, at least conceptually.
It does. I mean, there's a lot of delicacy about how it works.
Right.
but yeah, I mean, in a lot of cases, it's a. You can conceive of it as a VLIW machine, where you just have an instruction per AWG channel or per whatever else you need, and that works. That does work up to a point until you actually need to do some sort of conditional behavior. So, kind of state of the art is, well, I can compile a circuit and I can execute it as long as it's a straight line code, right? Like I have a basic block that's just executing straightforward, and then I do a measurement at the end, and that's fine. But if I need to do a measurement midway through the circuit where I actually have moved some of the ions out of the way, so I'm only measuring a couple of them, but the other ones retain their quantum information, and then I want to change the behavior of the circuit based upon that intermediate measurement, well, now all of those processors, how do you do control flow?
Right.
Which is, again, similar to how the GPU problem, if you've ever done GPU programming, you are basically writing giant SIMD type operations. It can be MIMD, but if diverging threads, right? If you have a program where some of the GPU processors are going take a branch one direction, but others go the other way. If you have a data dependent branch, that's a performance penalty there. In the quantum world, that's disastrous, right? It's really hard to model and figure out how that's going to work. And so that's an active area of development. What does an instruction stream look like for these machines to allow that type of operation? Because, as you mentioned, you have a friend that's working on quantum error correction. You need that kind of model. I need to be able to do some amount of work and then be able to look at a couple of the qubits to decide whether or not I need to do error correction.
Right. So you can't essentially it's unacceptable to introduce a stall because the system is just going to have looked totally different while you were not doing things.
Or if you introduce a stall, everyone has to stall, and you have to know exactly how, you have to be keeping track of the phase precession of every single qubit during that stall.
That makes sense.
Yeah.
Okay. So naturally, and this is also a little bit informed by listening to some podcasts interviewing folks from IonQ as well. But there is the GPU comparison is helpful here in that you don't want to do all computation on a GPU, right? So there are some operations that a GPU could be extremely useful for, right? I'm sure there are. I'm not aware of all of the different ones available for a quantum computer, but there is a portion of in the sequence of a program, right? There's a portion of it typically that is going to be massively parallel or something, but there's usually a lot of setup or tear down afterwards, if you will. And so what I've heard a lot in this kind of quantum computing space is folks talk about hybrid models, where you're kind of mixing classical and quantum computing. And, that brings up a lot of different questions, both on the instruction set front, right? So how do you model instructions that span across that? And then also on, an interconnect front, what is the speed between your classical and quantum computing there? What is the work that you're doing examining that space as well?
That is exactly what I'm working on.
Okay.
It's literally that exact problem, and trying to understand what levels, as you said, how close do you need to have the classical and quantum, and how do you exchange data and control flow between them? As you said, as we got to, you can't stalling instructions is on a quantum computer is really hard.
Hmm.
For more reasons than you might expect, right? Not only do you have to track the phase precession, but we didn't really cover this in the earlier in the physics part, but when you actually initialize the state of your qubit, it's only going to maintain coherence for so long. So basically, the quantum information will deteriorate over time. And so you only get a second or two
Hmm.
before the state's gone, right? That's as long as you can run the quantum program. And then there's also another dimension of the problem, which is that quantum computers are effectively analog. Like they're very similar to an analog computer in that you have infinite precision because you're ultimately moving that point around the sphere. You can literally move it in as tiny increment as you want, but there's error, right?
Hmm.
Just like when you had an analog computer and you build an integrator, there's error introduced just by noise of the op amps and other things going on in the system, or the tolerances and the resistors. Same problem in the quantum space. So you end up with fidelity. And so the number of gates that you can apply to a qubit introduces cumulative error until you get to a point where you can't actually discern what the output is anymore. So this is kind of the driving space of how much computation can you do, is how long do I have for coherence and how many gates can I run in that amount of time and still get a reusable result out. So box all of that with, and by the way, while I'm doing that in that 1 second interval, I want to take a measurement and run some computation on it and come back and change what I'm going to do.
Hmm.
So I can't stall for, a minute to go run a different classical operation and come back to it. I can't, waiting 100 milliseconds for a web service request to come back is just like, that's a tenth of my coherence window.
Right.
So you move closer and closer to the point of, well, do I start to introduce classical functional units inside of the FPGAs that are running this control system and actually have the treat it like the quantum operations are just specialized functional units, and be able to do sort of microarchitectural design of, passing data between registers and queuing it up so that, it did the measurement and then that's being queued into an ALU that's going to turn the result around. And like, that's one way of doing it. Or do you have a separate processor that's right nearby that, can punt the data back and run some straight line classical code and then push a result back the other way? And that's a very open area that is trying to figure out. And the answer is not clear, because
Hmm.
sometimes you want to have a model where the classical computation is what we call between a shot. So between those coherence windows, you maybe run 5 different runs of the circuit, which each has its own 1 second coherence window. And then you look at the results of those 5 to decide what you're going to change about it, right? You're doing some sort of statistical analysis. So you do a little bit of classical and then you do more quantum. But there's other times within like an error correction where you actually want to do that mid-circuit measurement and insert it, and different time scales get involved. So yeah, this is a problem that I'm actively working on, and the industry as a whole is working on, of how do you introduce these capabilities? How do you even build, like, what does it look like conceptually from like an instruction set standpoint is one
Hmm.
part of the problem. What does this look like from a language perspective is a whole separate problem. What does
Right.
this look like in a microarchitectural standpoint is a whole other problem. And then there's all the resulting problems that we create in the physics when we actually do classical computation and we're not running quantum stuff.
Right. So in the absence of kind of like this generalized computing model, or an instruction set or something like that, is most of the present day applications that are run on quantum computers, are they essentially like you're just rewriting the microarchitecture to do a very specific thing, or is there kind of like a interim state that we're in right now that allow us to do useful things on quantum computers without having a fully generalizable compute interface?
So the very high level, like circuit level with standardized gates
Hmm.
is where most of the algorithm research and like useful work is done. And
Okay.
so then it's internal compilation phases and things where it gets changed to the native get set and then basically does get compiled down to what would look like a microcode.
Hmm.
It's like a VLIW style microcode that's running. um,
Right.
and so that's usually hidden by whatever provider is you're using, right? Because most quantum computers today are as a service, not outright purchased.
Hmm.
So you can submit a job via one of the common frameworks like Qiskit or things like that, to AWS's bracket service, and it'll run on a simulator or on a quantum computer. And it basically, once it gets to the simulator or the quantum computer, that's where the compilation to the native instruction set happens. So it's a little bit isolated, similar to how GPGPU works, right? You write it against a more of a common language, and then it does that compilation behind the scenes for you. But the expression of how you interleave classical operations with quantum operations has traditionally been more of like the GPU kernel model, where I'm going to run, I write a Python program that builds a quantum circuit and then sends that off to the service. It runs it, it gives me the result back, and then I look at the results in my Python program and I do, a little bit of work, and then I submit another job. And so there's a lot of active work around how do you move that lower? How do you intermingle those classical operations more and make this more expressive, right? Like most of the time, you don't want to write just a quantum circuit and with a separate classical piece around it. That's, most of the problems that you start to look at are a little bit more complicated and intermingled than that.
Makes sense. So I think we're gonna have to have another check-in with you on quantum computing. Perhaps I'll do even more research and come with some more questions. But I definitely appreciate you being willing to dive in depth on that with us here. I did want to kind of wrap up by talking about some of the things I guess you do outside of your day job responsibilities. One of the things we chat about kind of like leading up to this chat is mentoring. And so like I feel like that as well as being on podcasts and something like that, one of the things that I feel like that I've observed through watching your work and your involvement in communities is your interest in like bringing other folks along on that journey as well. So I kind of just wanted to give you an opportunity to talk a little bit about what role that has played in your career and why that's important to you.
Well, I mean, as we covered, I grew up in rural Ohio. Like I literally grew up in around farmland. And so the chances of me ending up working in Silicon Valley at some of the, biggest names in computing is a wild story. I wouldn't have believed it if you had told me. Mm-hmm. And I recognize that a lot of that is luck and a lot of that is privilege. So even though I had all that luck and all that privilege, I also recognized that I didn't have anybody giving me any direction there. I just kind of stumbled through that whole path. And it was difficult. Like I just didn't have mentors. I didn't know people, and I couldn't ask a lot of questions. And until much later in my career, where I built a bigger social network. So quite a few years ago, I guess it'd be like 7 or 8 years ago, I started offering just public signups for people to do mostly mock interviews initially, but it kind of expanded into resume reviews and mentoring sessions of just, I've been in this industry for a long time. I've been a hiring manager. I've interviewed hundreds of people. I've worked at, the big companies. I've worked with VC. I've worked with startups, etc. Like, come ask me your questions. Like, where are you at? Are you trying to change from a different industry to come in here? Are you trying to graduate from a school and figure out where to go career-wise? Are you a junior engineer that is kind of reaching a limit with your current job and you want to bounce some ideas off? Like, I'm just happy to sit down and chat with folks. And it's really just to be that resource that I wish I had. So I don't, some folks do similar things, but they actually ask for, pay to compensate for their time. And for me, it's just, no, I'm just, it's free, right? I set aside a certain amount of time each week and have a sign up, and folks just do, and I show up and we just have chats.
That's awesome. I'm sure that's hugely impactful for a lot of folks. And, alongside that, as I mentioned earlier, you've also been pretty instrumental in going out and kind of sharing things that you've worked on. I know we already talked about y'all's DEF CON talk, but I came across a talk where you were detailing some of your work on engine motors, so things outside of your, although that does seem somewhat related to some of the control systems you've worked on, perhaps. But what's kind of your motivation for sharing your work more broadly as well?
And largely, I enjoy working on various things, right? Like cars is a hobby for me. I'm not a race car driver, that's not my profession. But do I enjoy driving on a racetrack? Yes. Do I like tinkering with cars? Absolutely. So when we get into where does that overlap with electronics and software and things like that, a lot of it is just I find it fascinating and I want to show other people what's cool about it and why it's an interesting problem, right? Like I suspect that there's a lot of folks who are just like, oh, my car is there, it takes me from A to B, and that's fine. And it's like, well, actually, there's a very complicated control system running under the hood that you don't know about, and all the different subtle things that are happening. And um, I don't know if you're familiar with the 99% Invisible podcast,
Yep.
but like the ethos there is finding architecture or design kind of out in the world or in different ways that are subtle things that you might not have really considered. And it's a similar thing here of, well, let's go find some of the engineering and things that you may not have seen, that I found because I found it interesting and I'm aware of it, and I just want to share that to have you think about it next time you are in your car, that there's actually a whole fleet of computers keeping track of how the engine itself is running and making that work. And it's a similar thing with coming and talking about quantum computing. Don't expect that a lot of folks are going to actively write quantum computing programs, but I'm sure you're all very interested in how it works now.
Right, right, absolutely. Well, one of my goals here is definitely for those folks who are curious about how things work. A lot of times, kind of like below the surface of the interfaces that we commonly interact with, that folks like you will come along and be willing to kind of go a little deeper down the stack and talk about what's really going on. So I appreciate all the times you've done that elsewhere, and I appreciate you coming by the show today and sharing your expertise on a lot of different topics here. It's been hugely informative for me, so I'm sure a lot of folks are going to get a lot out of it.
Yeah, well, I'm glad to have been available to come talk and share things.
Absolutely. All right. Well, I think we can probably wrap it up here. But Rick, thank you for joining, and have a great rest of your week.
Thanks.